Have you ever stopped to think about how we build the parts for some of the most extreme machines on the planet? We're talking jet engines, Formula One cars, things that have to be unbelievably strong. Well, let's get right into it, because the way we're doing it now is straight out of science fiction.
It really all boils down to this one huge question. How in the world do you 3D print something out of solid metal? Something strong enough to go inside a jet engine? I mean, we're all used to seeing little plastic things come out of 3D printers, but this is a whole different level.
The answer, it turns out, is pretty wild. It involves a revolutionary technique that doesn't carve things away from a block, but builds them up, particle by particle, from a cloud of superfine metal powder.
The official name is Laser Direct Metal Deposition, or LDMD for short. But here's an easier way to think about it. Imagine you have a super high-tech, incredibly precise hot glue gun. Only instead of a plastic glue stick, it's shooting out a stream of metal dust. And instead of a little heating element, you've got a seriously high-power laser melting that dust into solid steel or whatever you want right before your eyes.
So here's how the magic actually happens. A nozzle, controlled by a computer, sprays this metal powder. At the exact same time, a laser is aimed at a surface, creating this tiny little pool of molten metal. The powder hits that pool and instantly melts, fusing and becoming a solid part of the object. The whole setup then moves just a tiny bit, and it does it again and again and again, building the part up layer by microscopic layer. It's the total opposite of how we used to make things, starting with a big chunk of metal and cutting away everything you don't need.
It's an incredible process, for sure. But, and there's always a but, isn't there? This amazing technology has a big, expensive problem hiding inside it. It's not as efficient as you think.
Which brings us to the multi-million-dollar question that engineers are obsessed with. With all that powder being sprayed at the laser, how much of it actually gets caught in that molten pool and ends up in the final part? And how much just bounces off? In the industry, they have a term for this: powder catchment efficiency, or PCA. Here's a great analogy. Imagine you're trying to put sprinkles on a really small cupcake. You know how it goes. Some of them land perfectly on the frosting, but a ton of them just bounce off and go all over the counter, right? Well, PCE is basically the percentage of our metal sprinkles that actually stick to the cupcake.
And let me tell you, this is a huge deal. When you're using a special superalloy like Stelcar 65, that's a super tough material they use for turbine blades, every single gram of that powder is incredibly expensive. So any wasted powder is literally money just being thrown away. It drives up the cost and makes the whole thing less sustainable.
So this is where the science really kicks in. A team of researchers basically went on a hunt for the perfect recipe. They wanted to find the exact settings for the machine that would get as much of that precious powder to stick as possible.
And they narrowed their search down to two main clues, two big dials they could turn. The first was laser power. How hot do we make that little molten pool? The second was scanning speed. How fast do we move the laser across the surface? They figured the answer had to be in the combination of those two. So they did what good scientists do. They set up a whole bunch of controlled experiments. They carefully tested different combinations: low power, fast speed, high power, slow speed, and everything in between. They were methodically mapping out all the possibilities to find that one perfect formula.
Now, just to give you some perspective on what they were up against, the study itself points out that an efficiency of 40 to 65% is considered noticeably good. Think about that. Even in a good process, you could be wasting more than a third of your material. That was the benchmark they knew they had to beat. So, what happened? Did they find that magic combination? Did they crack the code? Oh yeah. The results are really, really cool. So the first piece of the puzzle came from the laser power. They found that as they cranked up the juice from 1700 to 1850 watts, the efficiency shot up from about 52% all the way to 64%. And that kind of makes sense, right? More power means a hotter, more stable molten pool that's just better at grabbing onto that powder. But the second discovery was even more critical. When they looked at the scanning speed, they saw the exact opposite happen. As the laser moved faster, the efficiency just tanked. It makes sense when you think about it. The faster you move, the less time the powder has to actually melt and fuse properly. It just doesn't have time to stick. And here is the absolute key takeaway from all their tests. While both things mattered, it was the scanning speed that had a much bigger impact than the laser power.
Controlling the speed was the most important thing for cutting down waste. Slow and steady really truly wins this race. So after crunching all the numbers and running all the tests, they found the absolute peak performance. They managed to hit a powder catchment efficiency of 69.08%. That isn't just noticeably good, that blows the old benchmark right out of the water. A huge, huge improvement.
And here it is, the secret recipe they were looking for. The perfect sweet spot was cranking the laser power up to the max they tested, 1850 watts, while bringing the scanning speed down to the slowest setting, 7 millimeters per second. That precise combination created the perfect conditions to capture the most powder.
And if you need any more proof that they nailed it, get this. The scientific model they built to predict all this was able to match the real-world results with a 98.52% accuracy. I mean, that's just astounding. It shows they didn't just stumble upon the answer. They truly understood the physics behind it. Okay, I know this might seem like a super specific, nerdy deep dive into manufacturing, but trust me, the ripple effects from this kind of discovery are absolutely massive.
The real-world impact here is just profound. Right off the bat, you're wasting less of these rare, expensive materials. That means manufacturing costs go down, which makes this incredible technology more accessible. It also means we can build stronger, more reliable parts for the things we all depend on, like airplanes and power plants. And bigger picture, every little bit of efficiency like this is a massive step towards a more sustainable way of making things.
And that really leaves us with this one big final thought. This whole journey was about taking something already amazing and just making it a little bit better, a little more perfect. It really makes you wonder, how many other huge breakthroughs are just waiting for us, not in inventing something totally new, but just in perfecting the incredible things we can already do?